think we can start. Thank you everyone for coming. So today we have Paolo Tenti this morning. He's Professor of Electronics and Power Electronics at the Department of Information Engineering of the University of Padova, Italy. His main research interests are in power electronics and industrial electronics. Currently, his work deals with power quality, distributed compensation techniques, and smart grids, with special emphasis to optimal control of distributed power sources. He has done many things in his career. He coordinated a national research program funded by MUR from 2003 to 2006, then 2005-2008, and 2007-2010, and currently serves as a member of national and international evaluation panels, including ERC and Eurostar programs. From 1991 to 2001, he was a member of the executive board of the IEEE Industry Application Society, and in 1997 he served as IAS president. From 2001 to 2008, he was director of the Department of Information Engineering, where we work, at the University of Padova. And from 2003 to 2008, he served as chairman of the Council of the Department Directors of the same university. Then, I should also mention that he's a member of the IEEE and is a fellow, basically an IEEE fellow. And in 2000, he was awarded the IEEE Millennium Medal. So we have an excellent speaker today. You will see it for yourself. It's not just a lot of medals and things, but he's really a top-notch researcher. He has always been a top-notch researcher, although in the middle of his career, he had to deal with a lot of administration stuff because he's good. And recently, he got back into the research. So he would like to keep an interactive sort of speech today. So if you have any question, you can stop it at any time. We'll be very glad to keep going and discussing with you during the presentation. Then we have 1 hour of talk now. Then we take a break for half an hour. In the break, if it's not too tired, you can also go and ask, because this is, as you will see for yourself, is a very interesting field. What he's going to talk about is to look at microgrids, so electricity grid, from a different perspective from what we have today. It's talking about energy land. So it's Internet of Energy paradigm. So you have these things that they produce energy, they generate energy, and at the same time are energy consumers. So they are called prosumers, like in the jargon that we have in this microgrid community. And this guy, they can basically exchange energy among themselves. They need to do it in a very energy efficient manner, and you will see the optimization problems that are behind there. Okay? So I will leave the floor to Paolo.
Thanks, Michele.
Thank you so much.
Good morning, everybody. After such a presentation, the only thing that I can do is to retire directly and leave the room. Yeah, I'll try to discuss with you what is going on in this area of microgrids and Internet of Energy, energy lamps. I have to say that all these definitions are not common in the community. There are no agreement on this definition. So I am trying to put something that in some way relates to other fields of application to more easily expand, which is the concept from energy to telecommunications or to other systems. Anyway, we are in front of a real electric revolution. You will see during my presentation that until February 2017, these were essentially discussion within the academic community with some experiments around the world. But after a move that the European Union made in February of this year, everything is becoming much more realistic, and essentially we have deadlines to implement a number of modifications that will bring really to the revolution of the electrical market. So my presentation is in two parts. The first one is essentially marketing information and discussion about the market of electrical energy. And the second part is on the optimization of these new entities that we called energy lands, and I will try to explain you the main difference between the current microgrids and what we see as energy lands. Of course, as Michele said before, if you have any questions, you can stop me anytime. It's much more interesting, I believe, to discuss in real time your questions than to go ahead and with a very annoying situation. Okay, let me show in the beginning some data from the energy market. This is a study, maybe some of you know the International Energy Agency, that every year produces a report on energy investments, consumption, utilization, and so on. And what you see here is the behavior you see along the years of the investments in renewable energies. And if you compare China, the other Asian countries that are not part of the developing these international, the 48 countries that take part of the Organization for Cooperation and Development in Economics. And then you look to Europe and the United States. There is something appearing clearly in this picture that Europe has definitely been investing more than the other countries in renewables. China is, you see, the numbers are increasing quickly, but Europe made a big effort since in the early 2000s, and with a peak in 2011. The reason of this peak is known to all Italians and Europeans, I believe. This is the term by which the incentives were reduced. So we had a tremendous politic of helping these developments, especially in terms of distributing renewables in the individual houses of European citizens, and this essentially had a stop or a reduction investment for that, the incentives, in the year 2011. From that point on, we had some reduction. But anyway, Europe remains the main investor. You see from the colors that we have solar, photovoltaics, essential applications that are taking the major part of these investments. Wind is also a main part. Hydropower, that is well consolidated, so the new investments are relatively limited, but we have huge plans for hydropower and other renewables that are biofuels and these things. It's interesting also to see how these investments were distributed, because here the definition is small scale and utility scale solar. These two terms, essentially, wind is normally investment for big players. It's difficult that small users invest money in wind energy because wind energy calls for significant plants. While for photovoltaic solar application, of course, small users, the end users, so-called end users, made significant investments. So you see here that these utility scale solar investment are smaller than the small scale investment. So normal citizens invested more than big players in solar energy. This is just to introduce the point that I will go in two slides from this one and the next. If we look to the European market of renewables, we discover that only 6% of renewable energy plants, power generation by renewables, are directly connected to the high voltage distribution. These are very huge plants and represent a relatively small percentage of the total. In the medium voltage, we have a connection of about 45 of the total power. Medium voltage are plants that, at least in Europe, are normally above 1 megawatt. Okay, they are connected directly to medium voltage. But essentially, 1/2 of the renewable energy is concentrated in the low voltage distribution lines. That means that are small users fed by the usual low voltage domestic distribution system, and they take essentially a responsibility over 50% of the total renewables in Europe. Okay, so the impact on the market of these small end users in terms of global numbers is very important. we have to say that so far the end users have been confined as zero meaning players in the market. So they have no influence on the standard committees, on the economical politics done in this, and their capacity to interact with bigger operators is zero. So far, this was the situation. In spite of that, we have that they take care of half of the production. If you look at the Italian situation in particular, we have a picture here in 2013, 2016. There are no big modifications for the reason that I said before. With the end of incentives, essentially the situation increased a little bit, not so much. The interesting point is that in Italy we have a total of 650,000 connections, and most of these ones, more than 550,000, are connections of photovoltaic sources to the low voltage distribution line. In economical terms, this means that more or less the Italian prosumers, prosumer is a name that means producer and consumers. So these are end users that have small production locally, normally photovoltaic, maybe with some energy storage, batteries, and are the same consumers. They are the usual people that pay the bill over the electricity bill. Okay, these people in Italy invested some 25 billion euros in their plants. The interesting point here is that this huge amount of money was directly paid by citizens. The mechanism of incentives is that slowly they have a return of investment that is not economically attractive. This is a strange mechanism by which the citizens are happy to participate to these mechanisms of improving the quality of energy because this improves the environment, and do not require, like big investors, banks would prefer, to have big returns or to have a plan of return on investment that runs in a few years. So essentially the return of investment for these people is 10 to 12 years. They invested a lot of money, and the result was that Italy reached the 2020 objectives that Europe defined a few years ago in terms of reduction of emissions, increase of efficiency in distribution, and increase of renewables without paying anything. So the government did with the same, if the government had released bonds, they had paid the same interest without getting the advantage of renewable energy in the system. So essentially it was a win-win solution for the government. In spite of those, at least in Italy, there is a big discussion on the negative impact of these small users that consume incentives. In practice, there was a big advantage for the government that had not to invest immediately this quantity of money. So, and this is general in every country. So the participation of citizens is in some way strange. It's not only dominated by economic factors, it's dominated also by a general attitude to participate to this improvement of the system, ecosystem in which we live. So this was the reason of this. Anyway, we have in Italy 550,000 users, which is the situation today. The situation is very simple. You have a contract, you are zero in the market, you have a contract that you cannot negotiate, by which you sell your produced energy at a given amount of money. You cannot discuss about this. So you introduce your locally consume or return the excess of energy to the distribution grid with a gain that is essentially very, very, very limited. So the role of this huge quantity of people for the moment has been essentially zero. There is also a big discussion on the advantages and disadvantages of having these heavily distributed system of power sources, because you know both wind and solar energy are intermittent by definition. The introduction of the injection of currents in many points of the distribution grid can alterate the voltage profiles. This can generate a reduction of power quality due to circulation of reactive currents. I don't know if somebody here is expert of electrical systems. This is some way my background. But there is an interesting point. We have a normative, the so-called grid codes, that are the standards that define the interaction between small users, the end users, and the distribution grid. Currently, it is requested that if you have a PV plant, you just inject in the grid the active power. This means that during the midday, essentially in Italy, the 22, 23 gigawatts that are produced and injected in the grid compensate large part of the loads. The only remaining currents in the grid are the reactive currents that are requested by motors, by many the so-called reactive loads that are currents, if you remember, do not generate average power transmission, but simply fluctuation of power. But this is not a matter of final users that do not operate properly. This is a matter of selecting the standards that impose this kind of operation. That is completely stupid, because as you will see later, end users can perform much better than this. But the standards require this one. So part of these problems are related to the standards, not to the incapability of end users to operate better. There are risks of islanding. This is a big problem, because it may happen that even if you want to isolate some part of the grid stays up, because there are local energy producers that keep up the voltage. Again, this is a high number of standards related to that. And then this is a real problem. The standard distribution systems rely on the fact that the power goes from, you know, which is the direction of the power. The power starts from the power station, crosses the transmission lines, goes down to the medium voltage distribution lines, at the end goes to the low voltage distribution lines, at the end to the final user. You exactly know in each point of the system which is the direction of the power flow. This is very substantial in order to allow protection of the system, because you know that if you open a switch upstream, essentially everything is downstream remains isolated. This is the basic mechanism of protection of electrical grids. That is in some way subject to criticism now, because we have injection of power in many points. So the power is not flowing from the power station down to the loads, it's flowing from many other points to the loads. So this can create, this is the main problem of introducing a high quantity of distributed power sources. Of course, there are many advantages in this. Of course, you can load much more, you can feed more loads with the same distribution infrastructure. One of the main problems that the distributors have today is that constructing new lines is very difficult. You get immediate opposition from the local population, because there is an expectation that every medium voltage line can generate horrible consequences in the health of the people. And so it's very difficult to construct new lines. So the idea to take the maximum from the existing infrastructure is very important. And of course, if you have local generation, this means that the average path that the energy has to flow from the power sources to the loads is reduced, because we have local generation, local consumption, the path is very short, and the main distribution lines are essentially reduce the load that they have to feed. This is a huge economical point, as I said before, and users participate to investments. Individually, they can put only a little quantity of money on the table for the game, but as a whole, they are speaking of millions of people in Europe. So essentially, they are an economical actor of relevance. And then distribution efficiency increases because, again, feeding the loads locally reduces the losses for transmitting the power from one point to another point. And this is the situation. In practice, we could get much more benefits by controlling in a more suitable way these distributed entities that today are enforced to a specific operation by the standards. So the problem here is we have all technical needs solved, but here is a problem of standards. If we allow a better control of distributed units, we can improve the power quality, the voltage stability, we can improve the power sharing among distributed energy resources, we can perform black start. Black start is the situation in which you have the grid that is down, and you have to start the grid from zero. This is a very complex situation, normally because, with synchronous generators you have to move them quickly, synchronize, it's complex. While with the help of electronics and distributed power sources, it's much more easy to help the grid to come up. And the same for managing islanded operation, that means operation in which you are disconnected, or part of the grid are disconnected from the mains, and then control demand response at the common coupling points with the utility, and also, very important, the increasing the hosting capacity for the same infrastructure. Hosting capacity means the number of the total power of distributed renewable sources that you can accept in an existing grid. So these are advantages that can be achieved with this kind of organization. In this moment, most of them are simply in a standby situation because the standards do not allow to do these things. Okay, vision. It's clear to everybody now that the current situation of distribution that lasts since 1 century, more or less, cannot resist to the various pushes that we have in this moment. Because all these problems that I mentioned before are becoming more and more complex with the distribution of power sources worldwide. We are not only in Europe, but you can extend this. When we have huge investments in China and in India and Brazil, these huge countries, the problem of managing the grids as it was done in the last century will not be feasible for a longer time. So everybody is looking at the smart grid, and the perspective to look in the smart grid are so many and so different. People in economics are doing a lot of work in that, to understand which are the best economical mechanisms to produce a return of investments for big players or small players to enter in this market. There are, of course, tremendous efforts for the managers of the electrical system to understand which means smart grid. And for all the other players, ICT representing a tremendous potential market and component of the market of smart grids to enter this market. So everything will change. But so far, it's not very clear how this will be changed. Everything is becoming, smart grid means two things essentially: distributed intelligence and distributed energy sources. These two things make a smart grid. But how to utilize these distributed energy sources and distributed intelligence, for the moment, is not completely clarified. There are many visions. The objectives to be optimized can be very different. It's very clear that there is a trend in some direction, but nobody, for the moment, has clarified which is the direction, because the interests in this field are completely different and possibly also in opposition with each other. And currently, people speak on transactive energy system, introducing the concept that these distributed power sources will have the possibility to enter transaction mechanisms that are not only transaction of energy, but transaction of money too, of services, of many things. So it is clear that some something will happen of very important, although is was not very clear so far in which direction. And now is the move from Europe that came in February. Before this document, this is a set of documents. It's called Winter Package. Really has a big, more institutional definition, but everybody called it Winter Package. Before that, the main document that we had in Europe on the evolution of the electrical market was those developed by Sigret. Sigret in 2012, if I remember, 2013, elaborated a document which is a roadmap for microgrid application from in the next 20 years, so until 2035, okay? And in the Sigret is an association of the big players in the electrical market. Transmission operators, distribution operators, big players. And in that document, essentially, the intervention as active actors in the market of the last end users, the small ones, was considered something to be discussed after 2030. So before there were many other things to focus for the development of the smart grid and the microgrids. Now Europe made these assumptions. First of all, by 2030, half of European electricity should be renewable. Okay, this is a significant increase over the objectives of 2020, for the year 2020, that were essentially 20% of renewable energy. Now we are going in the next decade to half of renewable energy. That means a big push in that area. Okay, but this is in some way only a figure on the impact of renewables, but much more. The drivers of the energy transition will be the consumers, not the distributors, not the big players. Those, the users, the final users in the electrical system. And these are only a few sentences extracted for this set of documents. Consumers and communities will be empowered to actively participate in the electricity market and generate their own electricity, consume or sell it back to the market while taking into account the costs and benefits for the system as a whole. So every single end user will have the option to play in the market. And every consumer will be able to offer demand response, that means respond to energy demands coming from the market, and to receive remuneration directly or through aggregators. So can join an aggregator. Aggregators are services essentially that aggregate people to sell their energy as a whole instead of managing individually every single user. But every single user will have the option to play alone or in aggregation with other users. It's much more because it's not written here, but in these documents there is also another assumption that every single European citizen will have the opportunity to play in the electrical market. That means that even those citizens that have not a photovoltaic panel in their house, they will be allowed to enter the energy market. In which way? For example, by buying energy storage devices, or by putting in association with other people to buy a photovoltaic field or a wind generator or something like this. So the option to enter the electrical market will be offered to every citizen. And this citizen, these end users, will be the main actors of the innovation. You see, every consumer or prosumer, not necessarily prosumer, because prosumer, you can become prosumer also by buying an equipment, not necessarily in your house, but even in another place, will be able to fully benefit from the market either individually or in cooperatives. And this is the new definition of renewable energy communities. No one of these elements is existing in the current regulations. These are completely new definitions. So this is really a terrific move, because this means that in practice, from your smartphone in future, you will be able to react to a demand of energy, decide if you wish to participate, can be an auction, can be a bid of any kind, participate or not, which part, in cooperation with entities that can be dynamic aggregations, and so on. So it's completely, you imagine at this point the role of ICT in this market. Essentially, we will have different layers here. The energy layer, energy production layer will be the basic layer, but above that, we will have a number of layers regarding new services, communication, control, measurement. This market is completely to be revolutionized by this kind of sentences. But so far, this was just an academic discussion. Before Europe made this decision was made by, not yet by the Parliament, so it's not a directive, it's just a document that was delivered by the European Commission, so the Council of Ministries in Europe, but then will go to the Parliament, and in that case will become a directive. So this changes the game completely, because so far we have been discussing within academics and maybe industries motivated to analyze possible news on the market, but now is becoming an objective of the European Union. And this is really, of course, behind that, there is the fact that in Europe, nations and companies have been exercised in this field for 10 years. So it's not coming up from zero, this. Germany in particular, and France too, they made experiments. EDF has been funding experiments how to manage these things. In Germany, they had the so-called e-energy program that involved 11 cities in various experimentations and so on. So behind that, there is a preparation that Europe is now ready to turn into application. Okay, how to get there? The question is, okay, this is the vision. At the end, everybody will be able to become a producer of energy and to sell this energy in the most free method that you can imagine. So there are many steps. Looking from the energy point of view, and then you will be much more able than me to look in terms of telecommunication or this kind of technologies. The first step that we see is the transition from microgrids to ELANs. First of all, the name ELAN, I don't, you know much better than me what is ELAN, and the name Energy LAN is exactly to expand the concept of local area network to energy. So not only exchanging information in the most proper way, with the due levels of security and so on, but also to extend this concept to energy. So local area energy, LAN is a local area, so a geographically limited area, where the participant, the energy producers, can physically interact, so they are connected with short distances between them. So the energy that I produce can go to Michele, who is 2 houses far from my house. And so this is a local exchange of energy, is a local community in which we can extend all the features of a LAN. So capability to communicate, to make decisions, to exchange energy, of course, in the most efficient way. Which is the difference with the microgrid? In theory, microgrid do the same. Have another name, but do the same. No, but here there are steps that are needed to go ahead in order to reach the level of ELANs in our vision. This is our vision. The previous slide was an European decision. This is our vision. The concept that we must introduce in ELAN that is not present in microgrids is the concept of power steering. So the capability to have the power flowing through specific paths. This has currently is not this is not an issue, essentially because we have only one utility connected to a microgrid, so you have to for sure to deliver the energy to that utility, and essentially the optimization schemes so far have been only limited to minimize the energy losses in the system. So the concept of controlling a microgrid is essentially a concept of maximum efficiency in managing the energy. But here we need much more. Essentially, we need to control the power flow at every grid port or section. For a number of reasons that I will tell you in a moment, this is what, in theory, you should do. Full control over the energy. Of course, even in presence of a limited set of controllable entities, you cannot assume that every single house in a quarter in a certain area of the city has the capability to have photovoltaic systems with inverters. So you will have some entities controllable, some not, some entities available to participate to the game, some entities not available, because including in the function of your control from the smartphone, you will have also the option not to play the game. And so we will have a limited set of controllable devices, but in spite of that, we wish to reach this situation in which can perform power steering. And this, from a topological point of view, requires a dramatic change over the current situation. Dramatic is simple change, but really is contrary to the mentality followed so far. That means we will need to use meshed grids. Instead of radial grids, all distribution grids are radial today. For the simple reason that when you open a circuit breaker, you know that everything is downstream will be will lose supply, will be go in a zero state situation. While if you have meshing in the grids, this means that you have many different or more different paths for the energy to flow. So interrupting the current in a point is not meaning that everything is around will at some point be released in a situation, in a zero state situation. So this is one step that is needed, and the other one is to implement not only synergistic control, that means taking advantage of everything is available, but also consensus-based control. Because every single user in the game will not be a slave in a system in which receives commands and execute the commands, but will have the option to enter the game in the way that he prefers. So the system of, you can imagine the control becomes a little bit different from what we had so far, because we have a topological complication due to the meshing of the grids and control complication due to the dynamic participation of these users that will change their rules and come immediately. And this new concept of power steering that is in fact relatively complex to implement. Please.
So about the concept of power steering, is it really necessary for to monitor that the power goes from one entity to the other entity? If you're thinking of just one-to-one interactions and very just very rare interactions, then this would be needed. But suppose we assume that there is power flowing all the time. There are many interactions happening all the time. Then the grid would be kind of so every user could actually just withdraw power from this LAN, ELAN.
Yeah.
And without, so there only a controller at the interface between the user and the grid would need to monitor how much power is being withdrawn.
In fact, if I can go ahead by one slide, I'll show you what we wish to obtain with this power steering. Power steering is a very general, okay, by the way, this ELN provides to be the technological infrastructure of Internet of Energy, that is the next step. But let me go ahead a little bit on why we wish to have power steering, and which is the meaning. The meaning is not, of course, that every single user decides how much, because locally you do what you want. This is not an issue. The problem is how you can control some specific lines that can be changed dynamically to achieve some goals. Okay? Okay. This, first of all, when we are speaking of power steering, we have to duplicate the concept in active and reactive power steering. So we can have these two entities that are decoupled, flowing through different paths. The reason is, for example, this is a tremendous step ahead in the logic of the European Union, that our ELN can connect to different utilities. And we can decide in every moment which utility will be fed from our energy. Both of them, but in which portion. There will be a dynamic demand response mechanism by which the utilities will make an offer, because we are changing the mentality here. They are not demanding, they will demand energy and making an offer for that, an economical offer for that energy. So in presence of different connection to different utilities, we will have a dynamic picture of the economical advantage in making a decision and the other one. So you see, we are up at least one level in the hierarchy of the system, because here we will have an economical goal. That reflects in technical requirements. So this concept helps in controlling the power exchange at a given set of grid ports. Another problem is that the participation of end users will be dynamically changing. And this means that we have to reconsider the available control variables in the grid and rearrange the control in order to perform, for example, what we want in these points. So this means that we have to, for the same result at the point of common coupling with utilities, we have to have the power flowing in different paths, and we have to control that. So at this point you understand that we have at least two levels of control here. We will have local control made by the end users that in some way make decisions and react to requests, and then a larger vision on the entire ELN to perform specific options. Other important facts are active isolation of faulty lines. If we have a meshing in the grid, we will not be able to stop faults except we isolate the entire grid. We open the circuit breaker and we remove supply in all the grid. That is a crazy way to proceed. While, if you have distributed control, you can drive to zero by control, electronically, the currents in the faulty lines, and then intervene, for example, by simply removing fuses that are physical connections that can easily be put in the end and the terminals of every distribution line, and allow insulation without insulating the rest of the grid. And this also requires that you remove the power paths from some lines and move to other parts. In addition to that, we have the usual problems that require in some way power steering. To stabilize the voltage profiles in all the ELN, you need to have the power flowing in the right way. To provide active compensation for load imbalances that is typical in low voltage distribution system, you need to divert the power from some phases and introduce the other one. In this way you can limit the thermal stresses in the feeders, because if you have a feeder that is overloaded, you can divert the power through other. And the same for the power stresses in the energy sources. If an energy is overstressed, a source is overstressed, you can divert, reduce the power and so on, and limitation of current stress in grid-tied inverters. So essentially, this concept of power steering in terms of application offers a number of functionalities that so far are not available.
So basically, the thing that you're explaining is like the management of the the power flow in the grid.
Exactly.
Okay.
In a way that is not the usual one.
Yeah, because
Okay.
it's very centralized right now. So
Yeah.
it's very
Exactly. We see discussing optimization, how you can run this. But really, we are putting together a number of objectives that are not usual in power flow analysis. Power flow analysis normally, first of all, is normally not applied in low voltage systems that are too distributed, too complex to deserve analysis with power flow systems. Normally, power flow analysis is made for medium voltage, high voltage system. In that case, you act on specific nodes in the grid in order to divert the power from one part to the other. Here, you can do this locally at a very low level and essentially in a very punctual situation. So, moment by moment, you can change the rules that you wish to apply. So you adapt control to what you have, what your dynamic goals are.
Also, I was thinking of the application like so ELAN as in the analogy with the communication network.
Mm-hmm.
So suppose house one, it's a person in house one has to send some energy trade with house 10. Then they send energy to that, but it's not necessary for the like a communication channel, a packet sent from one user to another user, that's very unique. It has to go to the particular user from this user, but energy is kind of
In fact, you have at least two layers here. One is the communication layer, and the other is the energy layer. Because in some way, controlling energy here requires a kind of interventions that are not specifically related to communication. So I can decide to have the power to flow through some specific path. I will send the information in the right places. Essentially, we will have a supervisor that decides how to move that. So the communication can also be relatively simple here because we don't need very quick communication because remember that everything is related to energy. In AC systems has a typical dynamics that moves from one cycle of the line voltage to the next cycle. So the response times are tens of milliseconds. So while for telecom this is very easy, you have many different ways to communicate safely with these time frames. For energy is much more complex. But anyway, the idea will be exactly what you are telling. I make some decision locally. The supervisor of the LAN will make other decision. We try to find an agreement, decide which is the proper set. This will be communicated around. Then the part related to power processing will have to actuate these commands. The integration of communication and energy is possible in the sense that the goals will be the same, but the mechanism will be substantially different. I believe the first one was there, then 1, 2, 3.
The question is, okay, you're saying we can change the topology of the network from a star to a mesh, but what about cabling? I mean, can we handle this using proper power electronics, or we need to add a large number of cables?
Large number, for sure. If we have a radial grid and we wish to meshing, we need to add the cables. But first of all, we are speaking on small areas here. Okay. We are not speaking on meshing the medium voltage or high voltage. Yeah. We are speaking on local areas. So cabling is for sure expensive. In the sense we have to spend money to add, but not necessarily lots of cables. We have not to have polynomial, complete polynomial, absolutely not. Maybe 1 or 2 additional cables can produce that level of meshing that is enough to ensure this one. I'll show you an example in which by adding 3 cables in a system that has 80, around a system of 80, we gain this advantage. Of course, as more dense is the mesh, as better in theory, as many options we have to have the power flow. But here we are not putting the problem in so general terms that we wish to absolutely control in every moment a number of things. In every moment we have some objectives. Of course, if we have a fault, this will become a priority to insulate that fault before entering the mechanism of demand response, for example. We can establish a series of priorities of interventions with the same available control and with a meshing that must be minimal if we are acting on an existing grid. Of course, if you are building a new area with new houses and so on, you have more option also to put these cables in the most reasonable way. Of course, meshing includes additional costs. The problem is that what you get in return of this investment is very high, because essentially what we wish to do here is to use every existing control capability, not to add new control capabilities. So take advantage of the plants that are already existing in the houses of the citizens. And so avoiding any additional investment that is not in communication and in improving control, so changing the control boards or changing the firmware for control and so on. So the investments on the side of energy will be very limited. The investments in the side of the distribution grid become, by the way, it's not necessary, strictly necessary to have a meshed grid, because you have many controllable sources. You can do almost the same, but of course meshing adds degrees of freedom that make you sure that you can face every possible situation. I don't remember, please.
Very quick question.
Mine.
Very quick question. I'm wondering if this type of agreement you have to, so the user doing a decision, the control center does a decision, so will that cause some sort of trade-offs in terms of latency? And in some critical applications it might be not possible. For example, if you're talking about healthcare, this type of communication might be not effective. How communication?
But frankly speaking, I don't see any problem with the communication, because everything we needed.
Power exchanging.
Power exchange. No, this is a bounded problem, typically constrained problem, because we have many constraints. Of course, consider that those constraints that come from the attitude of end users to participate to the game are essentially constraints related to the economical aspects. So, and this is essentially the same that is currently happening at the upper level in the market. So there is a request, and we wish to respond or not to that request. Consider that in a grid in general there are many options. There are many producers. We have energy storage. We can have access to the grid. So if we cannot get power from other places, of course we can buy power from the grid. So at the end, it is a dynamically constrained problem that requires a solution. But generally, the only real limits are those related to the physical limits. So you have some quantity of power. That is the power that you can deliver, no more than that. But a new part of the game that is coming up in these years very strongly is the use of energy storage. This can change completely the rules of the game, because energy storage decouples the problem of local availability of energy with the requests that come from the external world, in the sense that you have storage of energy and you can run this dynamically in the most proper way. So for sure is a problem that has many levels of complexity. So far has been run in the most simplest way. It was one king, the rest were slaves. So the mechanisms were very simple. Somebody was making decisions, the other one simply obeying this decision. Now the situation will change with a variety of responsibilities, and I imagine a variety of new players in the market, which will be the role of Google or such big players that have a tremendous capability to manage information, to make forecasts, to enter also economically on the market, to manage bids. So for the moment they are out of this market, or marginally look at this market, but in future this will be a big game. So I don't know anyway, this is my answer, but probably there are other options, other visions here. Please.
Yeah, I wanted to understand a bit more how the energy can flow from one source node to a destination node in this mesh, because based on also on the question by Nitish, it seems to me that it's really similar to our communication. It's a routing problem actually. So you have mesh network and you want to reach from one source to a destination. But normally in communication networks we have the packets that have an address. So in energy this is a problem. So the two layers that you mentioned, so the first one could be kind of communication level when the source and the
just to transform
make an agreement.
Exactly.
So the path is established and then the energy is flowing through this path. Something like this.
The second part of my seminar is related to how to manage this from the energy point of view, how to have the energy flowing in these paths that you wish. The control variables that we have available are essentially the controllable voltages that some of these users have available and the controllable currents that some other users have. So we have electrical quantities that can be controlled in amplitude and phase, and these are the mechanisms by which we can control the energy flow. Okay, so essentially we have a level of control that is unprecedented in electrical systems, because we are using the full power of power electronics that interfaces energy sources with the grid, that allows a very quick and precise control of currents and voltages. So we can locally in every node inject currents, control voltages, doing these things. And since it's like moving water, of course, if you have a little bit of inclination, the water goes in one direction or the other one. With the suitable synergistic control of these things, you can get this kind of...
The energy flow in the proper path.
Exactly, exactly. This is the objective.
Can I just add a comment to this, maybe on what your question is? So I don't think it needs to be a flow of energy.
Yeah.
Hello. Yeah. So I don't think it needs to be a flow from energy, flow of energy from one source to the destination. That's if so. Like if you visualize a bucket, it's already filled with water, and so if you consider that the ELAN is already, there are a lot of transactions happening. There is energy flowing all the time,
But it's not flowing all the time.
I think
Sorry.
we consider...
No, we will try to take the problem as a whole. So we have many sources, many control variables, many loads, many requests, and many boundaries all together. And we try to solve the problem as a whole, not managing directly the point-to-point decision. This can be one of the constraints that is in the problem, but what we will try to show in the second part of the seminar is how to manage this as a unique problem in which we have a set of goals, a set of control variables, a set of constraints, and how to manage this in order to get with a single solution,
Exactly.
everything. This can be updated at the typical frequency. You can imagine every half of the line period, that means you can update these variables. Okay? So, not a system of
It's not direct.
local, no. In order to manage this, when we speak about synergism of control, it means that we have local control capability and also great freedom locally to make decisions in the level of participation of the rest of the game. And then we will have a supervisory control. So locally you decide essentially what you are able to make available to the rest of the group participating to this. First you satisfy your local needs, of course, normally, then you say, okay, I can offer this current, this voltage, this power, and this has to be utilized in a better way for the entire community. So it's a layered problem, okay?
You can utilize the non-uniqueness of energy. The market is
Yeah, exactly. No. It's not a system of independent, we have to, because the main goals are common. We have ELAN goals and individual goals. Other questions? We are ready for the coffee break. Okay, the second step, how to get there, is a little bit more easy to understand. Because the technological basis is this capability of locally organize these ELANs in order to interact with the rest of the world. Then you can introduce other layers, and of course the result at the end will be something that is similar to internet. So this energy will flow from the low voltage to the medium voltage to the high voltage, from one nation to the other nation. At the end, by aggregation, you can increase this game, and essentially what is internet can be substantially translated also in terms of energy. So essentially, every single user will be part of a local community, but through the local community also part of a much bigger game. And this is the real interesting vision, because if you intend that at the end this energy will be something that can be transferred punctually and precisely, and sold in the market or buy on the market and aggregated, then you will have a number of new challenges. Of course, first of all is, from a technical point of view, integration of power and data network, because these two things must have to go together. And we will need new ICT platforms, set of new applications to manage this. This will be tremendous new market for not only for technology manufacturers, but for developers of software, firmware, of service providers. So this is a huge new world. Essentially, it's probably most of the elements that can make this possible are available. But you can imagine the level of at least new services that can come up with this new market. By the way, for electric market players that so far have been very resistive, very opposing to this kind of innovation, this is again a tremendous challenge, because it will be a paradigm shift in everything has been essentially consolidated in the last century. So everything will change there. The players, the system by which you manage and operate the electrical systems, the operators in terms of economical aspects. There will be lots of new enterprises in this area, not necessarily related to distribution and transmission. And so essentially is a new arena for many players and for innovative undertakings. This could be also for ICT a new killer market, because we are speaking of millions and millions of potential users and potential participants to this new market. So essentially, the challenge is very interesting, and Europe made a move that is very strong in this direction, because empowering end users to make active part of the market is definitely changing the rules of the game that so far has been followed. And of course, the ELANs are the technical instrument by which end users will be able to promptly, effectively, and efficiently share and trade energy, and not only energy, also services. Because this is for people working in power electronics, they can not only trade energy, but can, for example, help in cleaning the waveforms in the grid. So helping in making the quality of the power better. It is not related to exchange energy, it's related to the capability to work on high frequency waveforms that are typical of power electronics equipment and that are normally not considered in the standard market. So there are the function that's called active power filtering. These kind of services that can be provided locally and can help operations. So it's a new arena for with many challenges, almost for every player in the market. I stop here. Okay, this is the last figure. In the first part, I am very late, and but I can go faster in the optimization part because everybody here is very expert in these things. So this is the picture. We will have this local area energy network that will include what are normally called smart nodes, smart energy nodes. That means nodes where we have the capability to generate, possibly, or at least process energy, interact with the grid. We can have local control capabilities. We can have local energy resources also in terms of storage, and these nodes will interact within the local area network. Then you can imagine many of these networks. In a city you can have many of them, and then you can aggregate in upper and upper layers. So at the end you will have a cyber-physical layer where energy and data go essentially go together, and Internet will provide the cybernetic layer to manage all these things on a theoretically planetary situation. Of course, at this point we discover that many keywords like cybersecurity will be prime elements of this new game, because security of this transaction is absolutely fundamental, and also Internet of Things. This part of, of the physical world will enter dramatically in Internet of Things for the number of data, sensors, measurements, and exchange of data at every level. So this is a picture that starts from the lower physical level of energy and goes up to the level of management of the environment, or whichever you wish. Okay, I stop here for the first part. And you can take a break.
15 minutes?
Yeah.
11, we can start. Okay.
Yeah, excuse me.
Can I have a quick question? To please, to make your network ELAN work smoothly, what are the latency requirements of your communication link between?
As I mentioned before, here we need, for sure, security. So the communication must provide a high level of cybersecurity. I don't believe that we will need extreme performances in terms of bit rate, because everything is running very slowly compared to the typical speed of communication. The operation, the control of energy necessarily requires periods of the line frequency. In theory, you can control within a line period, this 20 milliseconds. No? But in terms of average power, everything runs on periods. So the current response times of any electrical systems are in the order of milliseconds or 10 of milliseconds. So communications, I don't believe, is a big problem because the information that must be exchanged is there. Of course, if we are speaking of reaction to faults or managing fast dynamics, this is mostly a power electronics problem rather than because you have to intervene locally. It's very difficult that you can manage a fast electrical transit by coordinating lots of actions. So probably at this point you will have the traditional passive protection system and essentially the active protection systems that are inherently constituted within power electronics devices. So in terms of this scenario, so managing energy in terms of negotiation on or demand response requires response times that are well within the capability of available telecommunication systems. Security will be a big issue because here the data can move energy. And of course, acting on the information system that controls this system can generate big losses in terms of big problems, in terms of economical losses, yeah.
Just to maybe be more comprehensive, you told me once that it could be more important in a high-landed mode, the speed of communication.
Yeah, depends essentially. Communication, the typical approach of people working in industry regarding power is this one, power and frequency, that means speed and energy. The approach is whichever energy, power capability, and communication speed you give us, we will find a way to use that. So, and this happens because this vision requires essentially relatively slow control. Locally can be very fast, but the coordination, the synergism is not requiring fast. But of course, if we had the capability to communicate much faster and in a very reliable way, we could think about reacting to fast dynamics, including faults, by using synergistic operation of distributed items. This would require much more rapid communication. So we are here in a level that is essentially economic. If we wish to move to control fast transients in electrical grids, of course this would require much faster communication between elements. But this is something that probably can be constructed during the years. Every kind of communication is available at a reasonable price, so within the economical convenience of doing these things, I believe it can be used. So if there is a very secure and fast communication system that allows to implement synergistic control algorithms very quick to manage situations that can be dynamic, generated by faults, change of loads, insertion or disinsertion of pieces, this would be extremely useful and can be used. For the moment, we are looking essentially at responding to demands and managing local fast dynamics.
Because most of us are from the wireless background. In your project in Iran, are you contemplating to use wireless links? I mean, are you contemplating to use this kind of wireless links?
Wireless is the natural application because we are on short distances. And wireless, by the way, has a big advantage over power line communication. Today, communication in energy lines is normally made by power line communication. But is that in Italy was discovered in a very hard manner. The inverters that manage energy that are available in these nodes generate lots of disturbances. So while in the old time the waveforms in the power lines were essentially sinusoidal at low frequency, so clean and power line communication was easy to implement. Now it's much more difficult because the noises generated by the power electronics operating, interfacing on the line in Italy currently are preventing measurements during the day. So essentially, power measurements in Italy are made, or better, communication from the smart meters to the central collectors of data. In this moment in Italy happen only during the night, because during the day, with all the PV systems operating, the level of noises generated by the inverters prevents every kind of communication. So in this sense, considering that inverters are operating at higher frequency and the power electronics component, the new ones, are faster and faster, we will have a spread of noises that will really cover wideband. So it's much more meaningful, I believe, in ELANs that are geographically limited using WiMAX or any wireless technology better than power line communication.
The station that is covering more or less probably all the area.
We are speaking of half a kilometer maximum distance, so you can run by wireless communication.
Yeah, and also I wanted to ask for you, Paolo, for the second part. What we are trying to do in this project, this guidance project that's here represented by these guys, is to, in every dot that you have in the video in the ELAN, we are putting, for us this is a base station basically. So it's not a human or a house, but would be itself a power base station which is powered by electrical energy from a solar panel with a battery and everything. We don't have a human behind it. Probably we have some policies, we have some software problem that is controlling.
But by the way, the solution to go in wireless domain instead of power line communication, of course, decouples also the energy platform from the communication platform. So the kind of regulations applied in some way become independent. So in a wireless domain, it's sufficient that every one of these nodes has a capability to simply interact wireless with the communication system. We don't need to take care of the fact that communication flows in the same lines where the power has to go. So we have much more freedom in terms of bandwidth of communication, because wireless can provide huge bandwidth that is much more difficult to get in power line, simplicity of equipment for controlling the communication, and completely decoupling from the geometry of the wireless system and that of the electrical system. So I believe that can be toward that interact just at the level of exchanging data, not necessarily to have physical overlap. But this is my vision, I don't know about.
Now it's time to take a break. We are left with 10 minutes. Sorry.